So this Quantum Fest is being celebrated in two ways, two modes. The first is this online mode, which is starting from today, and the next set of session, which is in offline mode, will be starting from April 22nd, 21, 21st to 28th, 27th.
Himanshu ji, can you increase your volume?
Okay. Yeah. So with this and this fest is being organized on behalf of IPTRC 19, and it's a pleasure that we have with us our president, our national president, AHLUWALIA sir as well. I'm seeing him. And our RC president, AMARENDRA sir. So I'll request first AMARENDRA sir to please introduce about this Quantum Fest first, and then we'll also ask for a few words by AHLUWALIA sir. AMARENDRA sir.
Yeah. Thank you, Himanshu ji. First of all, I would like to welcome all the respected dignitaries, colleagues, student friends, and all others who are attending this webinar on the behalf of RC19 IAPT, that is 19th Regional Council, Bihar. Now, the first thing is why we are interested in quantum. Actually, if you go into history, then we find that by the end of 19th century, actually, it was a common understanding among physicists that everything that could be discovered in physics has been discovered more or less, except for a few, one or two small things, which also will soon be discovered. Because by then, mechanics was almost fully understood. Electromagnetic theory, including light, then heat and thermodynamics, all these were part of physics. And generally, people thought that what else is there in physics? But they were in for a great surprise, because in the beginning of 20th century, a floodgate of new discoveries in physics took place. And that was basically the beginning of quantum mechanics and relativity, theory of relativity. And it is part of history now that whatever discoveries were made then have sort of traveled to many, many branches of physics as well as other fields of science. So, RC19 Bihar, we have decided to hold a kind of quantum festival just to make more and more people aware of the beauties of quantum mechanics and what are its scope today. Actually, this program will be in two parts. The first part will be from 10th to 15th, that is from today, and that will be sort of webinar type mode, every day 5:30 to 6:30, and we will have some eminent speakers and other people talking on different aspects of quantum. Then later on, actually 14th April has been declared as World Quantum Day. So this first part coincides with that, 14th April. And then we'll have another part in which there will be more of local participation in different schools and colleges and university departments, in which there will be lectures, maybe poster competitions and other activities wherever, whatever is possible. Again, for increasing the awareness about quantum. That will be during 21st to 27th. And incidentally, that also includes an important day, that is the birthday of Max Planck, who was considered as the father of quantum mechanics, you can say. And that is, I think, 23rd April or something. So we will have this festival. Now, quantum mechanics, again, what are the fields that have emerged and that have come out of quantum mechanics? In physics, there are many things like spectroscopy, atomic and molecular physics, nuclear physics, particle physics, solid state physics, plasma physics, statistical physics. Then we also have astrophysics, material science, electronics. Then there are some specific fields, quantum computing and quantum teleportation also, you can say, although it is teleportation not in the physical sense, but through information. Then in biology also, we have quantum biology. Chemistry is almost completely based on quantum mechanics. Then higher physics, quantum field theory, quantum gravity, quantum optics. Then quantum mechanics has also gone into neurosciences and many other engineering disciplines. So this shows that quantum mechanics, since its beginning in 1900, has gone quite a long way, but it still has to go a long way because it has opened up so many new fields. And one more thing, quantum mechanics has become rather a subject which is talked about in by philosophers and spiritual people, where they talk about idealism, and some of the schools of thought, quantum mechanics, they assume that this world is more than what we can physically observe. And so quantum mechanics there plays a very important part. In this series, we will have opportunity to go through some of the fields, not many, because it's just 1 week or less, 6 days to be accurate. We will try to get a feel of quantum mechanics, a little bit of understanding, a little bit of higher level things also, where people are doing research on the front line. It will all be a mixture of these. And now something more about quantum mechanics, because as far as a mathematical tool, quantum mechanics has established itself and people have been doing great things. But still, there's a lot of discussion and confusion and all that about why it works. To the extent that there are more than 20 schools of different hypotheses about quantum mechanics that people talk about. Most important or most common is, of course, the Copenhagen school. But there are others, many worlds and transactional and other schools of thought, which those who are interested in philosophy of quantum mechanics philosophical background, they take interest. It's still a muddle as far as the question why quantum mechanics works. And one more thing, many people are afraid of this subject because it is mathematically a bit tough and physically counterintuitive. But again, it is important because it gives results very close to what we have observed in nature. And more than that, it also gives your imagination a little boost. What might be the philosophical background of quantum mechanics? And a lot of scientists and non-scientists also have worked on that. I would like to congratulate you all because you have taken interest. And on the onset, I would like to thank all the resource persons, great people, who have agreed to contribute to this webinar. On the behalf of IAPT RC19, again, I will thank you all and hope you enjoy this webinar and take something from that. So, thank you.
Thank you, sir. Thank you so much. We have with us Professor AHLUWALIA, sir, the National President of IIPT. If I'm audible, sir, please say a few words.
Namaste, and I'm very happy to be part of this Quantum Fest. And I express my heartfelt congratulations to you for taking this initiative. It's a wonderful program which you have chalked out, and I'm looking forward to the lectures in it. I can see Professor Vijay Singh also sitting here, who is going to speak today. Professor Amarendra is also here, great. And there are good number of participants whom I can see. I think this Quantum World Day has offered us this opportunity to come together and present a program which will benefit a large set of stakeholders who are in our Indian Association of Physics Teachers and beyond. I think today the situation is such that everybody is excited about what is happening in the quantum revolution 2/3, and the way India is going ahead with the quantum mission. I think it is becoming very essential that we sensitize our students on the possibilities which are waiting for them to be part of this quantum revolution itself. This initiative is laudable, and I wish it all the success. Thank you very much.
Thank you, sir. Thank you so much. Now we have with us Professor Vijay Singh. Sir, are you comfortable? You can start your presentation now. You're muted, I think. You can unmute yourself.
आप अनम्यूट हो गया. कैन यू हियर मी?
Yes.
आपका फोन भी नहीं लग रहा है हिमांशु जी, आपका फोन नहीं लग रहा है. कैन यू हियर मी नाउ?
Yes. Yes.
Very
now
good.
you're
I'm very happy. How do I share my screen? I'm just going to share.
Yeah, you can share.
Okay, because I'm not familiar with WebEx. So first of all, before I share the screen, I would like to welcome Professor AHLUWALIA, who is so kindly taken time off to attend the sessions. And a big congratulations to RC19, Professor Amarendra ji, Himanshu Pandey for taking the initiative, and the RC19 office bearers who have taken an interest in this, in promoting a certain awareness about quantum, the new quantum age, I would say, the new quantum age. Professor AHLUWALIA made some pertinent comments about it, and I think Professor Narayan ji said something very nice, so something very useful, which may have escaped most of us, but I thought it was very well. He said he hit all the right buttons when he was talking about it. I personally am the wrong person for giving this talk. The sessions, from what I see, the program for these sessions are devoted to what is called the new quantum age. That is quantum computing, quantum error correction, quantum teleportation, and not the old quantum age where quantum mechanics was used very fruitfully to make devices such as semiconductors, for electronic band structure calculations, and for predicting the properties of elementary particles. Okay. That was no less a great achievement in the last century. But now we have something else about quantum mechanics, some questions that arose in the last century, but they were pushed under the carpet. So they resurfaced around the late 1980s, and now they have come to be very useful, so it seems. So the point is, I'm looking forward to the talks which will come now, either tomorrow, day after tomorrow, etc. And I will be following them very eagerly. Once again, before I begin, a very big thank you to RC19 office bearers, Professor Amarendra Narayan ji, Himanshu ji, आपको और जो भी यहाँ उपस्थित हैं उनको. And let me begin by sharing with you some key thoughts about the new quantum age, about some key thoughts which pitchforked or midwifed the new quantum age. Okay. So I will basically, my talk consists of only 4 slides and 2 introductory slides. So totally 7 slides, in which, without using equations, I would like to tell you what I think were the issues which prompted the quantum computing age and the quantum teleportation, etc., the new quantum age. So let me share it with you. Okay, here it is. How do I share screen? Screen share karna
Uh, you just go click the share button.
hai?
Share button and then.
शेयर तो कर ही रहे हैं लेकिन वो आ नहीं रहा है भैया. Okay, here it is. I hope this comes. Is this clear? Can you see this?
Yes, sir.
Huh? Just a little louder, so I would help.
Yeah, it's there. It's good.
So it says basics of quantum entanglement. Okay. So let me just begin with where Professor AHLUWALIA and Amarendra Narayan ji ended, and that is with the observation that light is a wave, and that was known around, well established around 1800s by Young when he used his double slit experiment. And what you see on the left at the top is the single slit diffraction pattern, and what you see below is a real life, what you say, a visible, visible proof of how waves add and subtract.
You are sharing a wrong screen, I think. It's
Why? What are you seeing now?
It's the Gmail.
Huh?
Gmail screen.
तो ये दिख नहीं रहा है मेरा some basics of quantum computing?
नहीं, ये Gmail screen दिख रहा है आपका शायद वो.
अरे यार, that is the whole point now. Now how do I share that one? Wait, well, I'll minimize this. अब दिख रहा है?
नहीं, अभी भी वही दिख रहा है.
तो कैसे इसको हम दिखाएं?
इसको आप शेयर स्क्रीन स्टॉप करिए.
Okay,
और
I'm really sorry, folks, for this because I'm very unfamiliar with WebEx. WebEx is something I've rarely used, in only once when I with Himanshu. तो शेयर स्क्रीन बंद करना होगा.
हाँ, इसको रोक के फिर डेस्कटॉप पे आपको आना है.
शेयर स्क्रीन बंद करे कि क्या
हाँ,
करे?
बंद कर दीजिए, बंद कर दीजिए.
शेयर स्क्रीन, okay. I don't know how to close it, but okay. Stop sharing now. I've stopped sharing now. Now tell me what. Now you tell me what.
अब फिर से शेयर पे जाइए. जब शेयर पे आइएगा ना,
हम्म.
तो आपसे ऑप्शन मांगेगा. तो आपने कहाँ रखा है वो फाइल? डेस्कटॉप पे होगा ना.
अरे वो तो इसमें है ना, वो तो आ ही नहीं रहा है इसमें.
तो उसको डेस्कटॉप पे ले जाइए.
I don't know what you mean by desktop here.
आप कहाँ रखते हो वो फाइल?
यहाँ मेरे इसमें है यार. Here it is. It's right on here.
तो आप शेयर में दिखा सकते हैं उसको.
तो आई दिख ही नहीं रहा है तो मैं क्या करूं? हाँ, आ गया. Now let us see if you can see. Is this clear?
Yes, now it is
Okay,
clear.
thank you. I'm really sorry, Amarendra ji and Professor AHLUWALIA and the entire audience. You know, I'm not familiar with WebEx and we should have joined a little earlier to try it out. Okay. So this is basically a talk, as I said, which will consist of only 4 slides and 3 introductory slides. And what you're seeing right now is the first introductory slide, something that we are all familiar with, that light is a wave. What you see on the lower left-hand side where my cursor is basically what you do is you take 2 stones, drop them at nearby points on a still pond, and what you will see is waves adding and subtracting each other. So what these nodal lines that you see are the waves which are subtracting each other at these points, the 2 waves from the 2 dropped stones. So these nodal lines are a destructive interference, so to say. And what you see as outgoing waves, I mean these crests and troughs, these are the addition of the 2 waves. Okay? So light is a wave and you establish it by showing that it behaves the superposition principle and it shows destructive interference and constructive interference. Okay. Okay. Light was also found to be a particle, or at least predicted to be a particle, very tentatively by Einstein when he proposed that to understand the photoelectric effect, you must endow the photon or light, or you must view light as packets of energy with a well-defined energy and a well-defined momentum. Okay. And the momentum of the photon is precisely given by this formula, a very simple formula. P is the momentum, so you know that it's a property of a particle. On the right-hand side, you have lambda, which is the property of a wave. And what joins the two together is a constant known as the Planck's constant. And as Professor Amarendra put it, we are going to celebrate Planck's birthday on the 14th of this month. Okay, so this reverting back to the corpuscular nature of light, or to a particle picture of light, was proposed by Einstein around 1905. So if this be the case, de Broglie proposed, says, about 18 years later, and exactly 100 years ago, that a particle will also behave as a wave. So associated with a moving particle is a wave. Okay, so this is de Broglie's proposal. Sorry. Okay. And what he said was, if there is a particle which is moving, you can think of it also as a wave getting associated with it. Now, this is hard to believe. There is something like a very solid particle, and then you associate with it something which is as nebulous and unclear, and something that you can hardly imagine, a wave. But if you accept this thesis, if you accept the thesis that a particle also has a wave character, okay, right, then you can explain a whole lot of dilemmas that existed in the world of physics around the 1920s. So the big crisis in the field of physics occurred basically between 1900 or 1895, if you would like to believe, put it till 1925, when de Broglie proposed and then Schrodinger derived and Heisenberg obtained a mechanics, developed a mechanical theory or developed a dynamical theory. I'm sorry, not a mechanical, but a dynamical theory for the quantum microscopic world. Okay. So what is the idea I would like to leave with you? That associated, now get this very simple fact in your mind, associated with a moving particle is a wave. What is the wavelength of this wave? It is nothing but h divided by m times v, that is h divided by the momentum of the photon, of the particle, m into v. So on one side, you have a particle nature, say lambda, wavelength. On the other side, you have, on one side, you have the wave nature, that is lambda. On the other side, you have a particle nature, that is momentum, mass times the velocity. Okay, let's get this clear. And with this, you can push ahead. And merely by this fact, you can understand a whole lot of things, which I have listed here. I mean, this is to say that it was a mangadant vichar nahi the. This was not an imaginary thing. This is not a very thing which was just purely philosophical. I mean, it had real life implications. In one case, you can use it to make the electron microscope. Okay. Because just as you have a light microscope, the electron, when it is moving, is a wave, and you can actually image things using the electron microscope, using these electrons. Okay. Right? These things are actually done. The electron microscope is used very heavily in biology. Okay. Basically, not in vitro. I mean, in the sense it is used only on dead particles, because you need to have a vacuum for the electrons to travel, a very good vacuum. So you have only dead tissues or dead particles or dead cells which are imaged, but you can nevertheless do electron microscope. In addition, you can also understand crystal lattices based on neutrons. When the neutron is like an electron but much heavier, it is 2000 times heavier, you can use the neutron and the wave nature of the neutron to image a crystal structure. Particularly, it is particularly useful for magnetic structures. Okay. Why magnetic? Because the neutron has a magnetic moment. So when it interacts with certain magnetic solids, it can image them quite well. You can even image the DNA molecule. And this is not the end of the story. Just using this formula, which is written over here, lambda is equal to h by mv, you can even etch submicron structures. In the sense that we don't just have the quantum mission, we also have the mission to design and fabricate chips. The Indian mission to design very high-end chips can be done using particles as waves, electrons as waves. So submicron nanostructure is also etched by using this property, lambda is equal to h by mv. Now I want to leave you with a single thought, that these one is that these are not imaginary things. These are actually been accepted. This has actually been developed for the last 50, 60 years. And the second thing is that it uses very little of physics knowledge. You just need to be familiar with this concept that lambda, the wavelength of the particle, is inversely proportional to the momentum of the particle. Just that. Because if you talk to a biologist, he doesn't go beyond this. He doesn't understand quantum. He doesn't understand Schrodinger equation or a complicated solution to the many-body Schrodinger problem. What he does understand is that lambda is equal to h by mv. So if he increases mv, lambda becomes smaller. His resolution becomes better for his microscope. So ultimately, what you have to give the engineer or the biologist, okay, or to a understanding person who's going to use it, is just the final empirical thumb rule that lambda is h by mv. Okay. So having said this, my introductory part of the talk is over, and now I will tell you what are the implications, how to basically understand the lectures which will follow in quantum computing and quantum error correction in the days to follow. Okay. So let's accept the fact that the particle is a wave. So what, you will say? So one is that a very important point is that identical particles are indistinguishable. This is point number one. I want to basically get across to you that if two particles are identical, then in quantum mechanics, they will be indistinguishable. This is very much unlike classical observations. If you have a billiard ball and two white balls collide, you can normally understand which ball went where. The left ball went to the left side and the right ball fell into the right pocket. Okay, or they exchanged. They had a glancing collision, so the left ball went to the right and the right ball went to the left. You can actually distinguish two identical balls. When you play a carom board and there are two white coins colliding, you can definitely see and observe which carom coin went to the left, which went forward, which came to the back. Okay. But in the field of quantum mechanics, if there is one particle and another particle and they collide, okay, two electrons collide, you can never say whether the first particle went over here or the second particle went over here. Why is that? Because the particle is essentially not a particle but a wave. So when these two waves come together, this question mark then makes it clear that you don't know what's going on there. It's a wave, it's a hazy picture, and then as they emerge out, you can never say whether the particle going to the top right is particle 1 or it is particle 2. The particle going to the bottom left is particle 2 or particle 1. Why is that? Because you don't have a particle. You have a wave with a certain extent. So when they collide, you don't know in this blur which particle is where and which one goes. So as long as they are identical, they become indistinguishable. That is point number one that I want to leave you with. Identical particles are indistinguishable. Okay. And well, there's a quote by Feynman that I have here, but I don't want to belabor it because I think you all know about it. What Feynman said about quantum mechanics is that how can you have a lambda on one side and a momentum on the other when you ask such a question? He says, I think I can safely say that nobody understands quantum mechanics. Okay. So lesson number one, identical particles are indistinguishable. How do you argue for it? A simple way to argue for it is to say that there's no particle, there's a wave. So when they come together, you don't know which wave is where, which particle's wave is where, and where does it go. Okay. So it's like a black box when it is colliding. Next, lesson number two. Okay. Electrons, like the neutron that I mentioned, the proton and the electron, they all have a magnetic moment. Okay. Right. And therefore, in a loose sense of the term, when speakers who follow tomorrow or day after, when they say the electron has spin, they don't really mean that the electron is an extended body with a charge and it is spinning. No. When they say it has a spin, what they actually mean is that it has a magnetic moment. Okay. Why do they loosely speak of it as a spin? Because we now know from classical physics, we all know, if you don't, I'm reminding you about it, that if there's a circulating current, okay, there will be a magnetic moment associated with it. What is that magnetic moment? The magnetic moment mu is nothing but the current into the area of the loop. Okay. Similarly, what is the magnetic moment of the electron? It would be the charge of the electron and some kind of angular momentum associated with the electron. Do not get the impression that the electron is actually rotating. It is not. Okay. It just seems to have, it just has this one property of charge, which is 1.6 × 10⁻19 coulombs, and it has something called a magnetic moment, which is actually very small. It is something like 10⁻23 joules per Tesla per electron volt or something. Okay. So this happens to be a property of the electron. अब इसमें एक और मजेदार बात है. There's something very interesting about the electron having a spin, and the interesting thing about the electron having a spin is that this electron, okay, which has a spin, can have a spin either oriented in up or it can be oriented down. Okay, it can only have only two orientations. It cannot have any which way. It is not like your bar magnet. You take a bar magnet, show it to your kid or to show it to yourself. You can orient the bar magnet in whichever direction you want. Okay, so the magnetic moment may be pointing in another direction. Then you can orient it in the northwest, then in the east or the west, then southwest, and then south. It's not that you can orient it continuously. Not so for the electron. If there is a spin and you decide to measure it, it will be either up in that direction or down. It cannot be perpendicular to it. Okay, so this is the second fact that you must remember. Electron has a spin. It doesn't mean it is spinning. It means that electron has a magnetic moment, and this magnetic moment, when you measure it, can be either +1 in some unit or -1. Okay. Any questions up to this point? So there's two lessons so far. First lesson is identical particles are indistinguishable. The second lesson is that electron has a spin. Okay, electron has a magnetic moment, and when you measure it, say in the eastern direction, then it will be pointing either in the east or in the west, not in any other way. It's not a continuous orientation. The only orientation possible, if you decide to measure it in the vertically up direction, is that it will be vertically up or it will be vertically down. Okay, it will not be oriented continuously. You will not get it in any other direction. Okay? That is lesson number 2. The spin can take only two values. The magnetic moment can take only two values. Lesson number 2. Now lesson number 3. Okay. Oh, well, not this. Okay. The lesson number 3 is something very peculiar about measurement theory in quantum mechanics. Very, very strange in quantum mechanics. And this is where Einstein became very uncomfortable with quantum mechanics. And he even wrote a very famous paper. The paper is called EPR, Einstein-Podolsky-Rosen paper, in which he voiced his concerns about the quantum theory. Now, what was this concern? How do I explain it to ourselves? How do I explain it to our school kids or to even our college undergraduate kids? This is one way to explain it, perhaps not the best way, but one way. Think of a particle in a box. Assume that you are in a room, wherever you're sitting, and there is some ball right in the middle of the room. Here is a picture, a classical picture. Here's the classical picture. This is a box. This is your room, and there's a ball. There's a ball in the middle of the room. Okay. Now the room is closed, say, and somebody decides to enter the room and see where, and wants to verify where the ball is. What will he or she see? She will see the ball here, finished, in the room, in the middle of the room. Okay. So assuming that there's a room, you're sitting in one room, assuming that there's a neighboring room and there's a ball lying somewhere over there. Okay. Right? Where it is, you don't know. How do you verify this? When you go there and you open the room, you will see it. As simple as that. There is no surprise in this. In classical measurement theory, there is no surprise. Okay. The only surprise that happens in classical measurement theory is the following. Okay. But it's hardly a surprise. And let me just point out to you. For example, I want to measure the temperature of water which is boiling. I'm making tea and I want to measure the temperature. I want it to be not 100, but say 80 degrees centigrade. Okay. How do I do it? I'll put a thermometer inside it. When I put a thermometer inside it, the heat capacity of the thermometer will also contribute. So when it shows 80, it means that the temperature of the water was about 80.1 degrees centigrade. 0.1 degree centigrade was taken up by the heat capacity of the thermometer, so to say. Okay. The point in classical measurement theory is, yes, they believe that a measurement disturbs. A measurement is disturbing the system. It is not as though you will not disturb the system, but that disturbance can be minimized as much as possible. So when I put the thermometer inside the water, the thermometer will absorb some heat. But I can make the heat capacity of the thermometer very small so that this absorption is small, and I get a very, very accurate measurement of the temperature of the water. Okay. So similarly, oh, sorry. Is this clear? I mean, is my slide visible or not? That's what I'm very worried about here. Is it? Can you see the slide?
Yes, sir.
Okay, take care. So that is classical theory. Now look at the quantum theory. The same particle in a box, right? I've already told you, we have already learned together that there is no particle, but there is a wave. This wave, but the wave might be a single, I mean, like what I would call as either fundamental or the first harmonic. Okay, but it has to be a node at either end. Okay, and the wave could be this semicircular shaped one, or it could be a contorted one like this. This wave is called the wave function. And the modulus square of this wave function is where it's called the probability where you'll find the particle. Now, since there's no such thing as a particle sitting in the middle of the room, but there's a wave, what happens if I enter the room and I see? The answer is the same as classical. When you see, you have to find the particle somewhere. You will not find a wave floating around in the room or something. You'll find the particle somewhere. Okay. So you'll find the particle either in the middle, which means that this wave function that you see has collapsed. Okay. To something like a delta function or something like a very sharp Gaussian or something. Or you might see it here. You could see it anywhere you want. Okay. We don't know where, but you'll definitely see it somewhere. And what this would be like, the wave function has collapsed around this point. So when in quantum theory, when you measure, you disturb the system and the wave function collapses instantaneously to where you have seen the particle. Let me repeat this thing again. Classical theory of measurement and quantum theory of measurement are very different. In quantum theory, there is a wave, but when I actually observe, then I'm going to see the particle at a certain point. And when I see the particle at that point, it means that the wave function, which is a measure of the probability of finding the particle, okay, the wave function has actually collapsed. Okay. And this has collapsed instantaneously. You might say, why are you insisting on instantaneous collapse? You insist on this because you have no intermediate theory. If you say, no, it is not instantaneous, then I would ask the next question. Then how does it collapse? What is the time evolution of that collapse? Where is your theory for the time evolution of the collapse? So the Copenhagen interpretation, which was alluded to, I think, both by Professor AHLUWALIA ji and Professor AMARENDRA ji, is that there is going to be an instantaneous collapse of the wave function. Okay. This is something that Einstein found very hard to believe. In fact, at one point, when he was walking with a friend of his in a garden, and it was night, I mean, it was nightfall, I mean, and then he says, this is as strange as saying that the moon only appears when I look at it. So it's a very famous quote, does the moon appear only when I look at it? That's what Einstein asked. Obviously, it doesn't happen. It means that if the particle is to be found here, look at this part. It was always there, you would say. That is what Einstein would say. But what the Copenhagen interpretation says is no, the particle could have been anywhere, and when you observe it, you make it collapse. I mean, that is to say, your observation actually disturbs the system dramatically and instantaneously. Okay. Now I'll stop at pause at this because this is my third slide. If there is any comments anybody would like to make, I would be very happy. Okay. So let me go back to the three. One is that identical particles are indistinguishable. The next is that the electron has a spin, which when you measure it in a given direction will be either +1 or -1. Okay. And the third is that there is instantaneous collapse of the wave function when you measure it. Okay. Right. So now comes to the fourth and the last slide, okay, which is at the heart of what is known as the EPR paradox. and which is at the heart of quantum entanglement, and which is what basically has pitchforked or midwifed the new quantum age. Okay, it's given a boost to it. And that is EPR, or quantum entanglement. Okay. Now, who formulated this? The first version of this, the EPR version of it, is something which is hard to comprehend. So there is a version of it that was basically proposed by David Bohm, and that is the David Bohm version is what which people normally use to explain the so-called EPR paradox and quantum entanglement. What is this version? What Bohm said was that you take two electrons in a singlet state. Now let me explain what I mean by this. He said you take two electrons, the electron can be either up or down, but you now prepare the electron with zero angular momentum. That is to say, if one electron is up, let the other one be down. Singlet means angular momentum is zero. Singlet means there is no net magnetic moment. The two electrons are conjoined and they have been prepared so that the net angular momentum or the net magnetic moment of this two electron system is zero. Okay, so that is what is meant by the first statement in a singlet state. I have deliberately plotted, for ease of understanding, the three axes: x-axis, y-axis, and z-axis. That means that because the system is indistinguishable, these two electrons could be up or down, that is in the plus z direction or the minus z direction, we don't know. It can be to the right, that is in the plus y direction or the minus y direction, or it could be in the plus x direction or in the minus x direction. Okay, it is in a singlet state. I've prepared it. Okay, I don't know which one it is. Plus x, plus x minus x, plus y minus y, plus z minus z. Now I take these two electrons and I separate them. I pull them apart, send one of them, for example, if I'm right now sitting in Mumbai, I send one of them, say, for example, to Beijing and the other one to New York. Or for that matter, you can send one to the moon and the other to the Mars, to the planet Mars. You just put them, throw them far apart. And one of them, say, for example, the person who is sitting on the moon, decides to measure the spin of the electron along the z-axis. Okay, if he or she measures it, sorry, I'm not able to understand. 1 minute. Now, if she measures it, she'll see either along the minus z direction, correct? And in that case, what will happen? Instantaneously, the other one will turn out to be in the plus z direction. So the other one doesn't have to measure it in Mars. Okay, all that she has to do is to communicate it to the Mars person that I've measured minus z. Without measuring, the other person will know that it's in the plus z direction. Or supposing she gets it in the plus y direction, doesn't matter. Okay. The other spin automatically goes in the minus y direction. That is to say that it is very strange. Okay, it's almost like saying that if you have a red ball, say a red marble and a black marble, so say a white marble and a black marble, and you put it in your two fists, okay, and then you open up one fist, it turns out to be white, the other one is black. But it is not as though it's like saying that what you had became white only when you opened your fist. It was not white all along. Okay, so the point that Einstein was making is that I could have decided to measure it either in the x, the y, or z direction. How come the other one will turn back to the other in the opposite direction, to x or y? How will it be complementary to it? Either it is always like this, or it becomes complementary at the last moment. Hard to believe. Okay. It's like basically the so-called Hindi movies that you see when you have these two twins and you pinch one and the other one is hurt immediately or something. He also feels the same pinch. Okay, so it is this nature. Now, does this really happen, you might say? Okay. How do you test it? The answer to that is there is a test for it that was devised by John Bell in 1964. Okay, predicted by John Bell that you could do to test this entanglement theory, to test this instantaneous collapse of the wave function, to test the fact that I can send a signal across the globe at a speed faster than the speed of light. Okay, this test by John Bell was verified by several experiments done in the late 70s and 80s. Quantum mechanics was found to be correct. It is indeed true that there is something called entanglement. If there is one electron here, the other electron, howsoever far away it is joined to this and it's got to do things which it's got to behave in a complementary fashion to the first electron. So what you do to the first electron, the other electron gets affected. And that's how you send messages across, and that's how you do things. Okay. So with these 4 slides, okay, let me rest my case. I repeat again, there are only 4 points. Identical particles are indistinguishable. Electrons have spin either up or down. Okay. Measurement theory means that there is instantaneous collapse of the wave function. And number 4, there is entanglement. Okay. The famous EPR paradox, Einstein-Podolsky-Rosen paradox, stated in terms of 2 electrons by David Bohm. Okay, I'm done. Thank you. Hello.
Yes, sir. Thank you, sir.
Okay.
Now the participants can ask. They have any.
Should I stop sharing?
Yes, sir.
Okay, I'll stop sharing. वो stop sharing कैसे होता है? हाँ, yeah. Stop sharing हो गया. हाँ.
Yes. If you have any question, you can raise your hands. I'll unmute and you can ask questions.
Okay. So certainly it's not a very clear lecture, and I'm
No,
certainly no expert.
It was very nice. I had, sir, one question
बोलिए.
about this different जो एक measurement वाला slide था.
हाँ.
Those
जी.
two say diagrams B and B prime.
हाँ.
So B and B prime का जो difference था, वो क्या था वो difference? There was only the difference of location or something else?
No. Let me share it again then, because I don't. It will be hard to. There's one. ये दिख रहा है? कि नहीं दिख रहा है?
अभी नहीं दिख रहा.
जी?
अभी नहीं दिख रहा है.
वो नहीं दिख रहा है. So how do I share it? I mean, this is getting a little problematic. Okay. What do I do? I forget.
Share.
Oh, I'm going to. I want to share it. Share कर रहे हैं. I'm trying to share it. Share. Screen ना? Screen ना?
हाँ, screen share.
अरे फिर से वो नहीं आ रहा है. फिर समझ में नहीं आती क्यों नहीं आता है.
बीच में आपका शेयर है, उस शेयर को बीच वाले को वो ये करेंगे.
वही हम करना चाह रहे हैं हिमांशु जी. And I'm a little upset that I can't. This is very different from either Zoom or. एक minute. Give me a minute. I'll share it now. Can you see it now?
Yes.
ठीक है. तो अब क्या करना?
This ये जो instantaneous calculation वाला था, instantaneous collapse वाला.
जी.
तो B और B prime का difference
नहीं. कहने का अर्थ है कि this is the wave function. अब wave function का square जो है वो probability density देती है particle कहाँ रहेगी. तो अगर wave function is like this, then the higher probability is in the middle, say, correct? But if the wave function is in the first excited state or the first harmonica that is called, then the particle probability in the middle is 0. It's higher here or here, correct? So depending on where, I mean, but it can be here. I mean, the particle can also be here. It's not as though the probability of finding the particle to the left side is less than the right, than the middle. It's less, but it's not 0. Okay. So when you measure, you don't know what you will get. You will get that the particle was in the middle. You'll get the particle was to the left, B or B prime. You can get it to the right. But you have to get it somewhere. No? After all, measurement means you're going to get a number. You're going to see something. So it is not as a quantum mechanics where you don't do the measurement. But what the measurement does to the wave function is does a lot of violence. Okay. वो बड़ा अत्याचार करता है wave function. Wave function को तुरंत बदल देता है. हाँ, जबरदस्ती से. So observation disturbs the
Changes.
system catastrophically. यही कहना चाहते. यहाँ रह सकता है, B हो सकता है, B double prime हो सकता है. You don't know what's going to. There are many possibilities between the two ends of the box.
And the second excited state will be more drastic.
Yeah, I mean it can be anything. So वो हो जाता है.
अच्छा, ये इसके आगे वाले स्लाइड में सर इलेक्ट्रॉन के सिंगलेट के बारे में बात हुआ था. इसके बाद हाँ इसमें ये जो जैसे बोल रहे हैं इलेक्ट्रॉन्स इन अ सिंगलेट स्टेट.
हाँ.
So that is the only possible state या एक
No. What he's saying now, you think of what Einstein did. What Einstein is very famous for is doing what is called Gedankenversuch. वो जर्मन शब्द है. उसका मतलब है थॉट एक्सपेरिमेंट. वो मनगढ़ंत एक एक्सपेरिमेंट बना रहे कि मान लीजिए कि इफ देयर इज एन इलेक्ट्रॉन इन अ सिंगलेट स्टेट, एक ऊपर है और एक नीचे है. मान लीजिए ऐसा. ओके, सिंगलेट स्टेट मींस यू प्रिपेयर इट इन दैट स्टेट. वैसा आप बना दीजिए. आप कर सकते हैं. यू नो, जैसे कि आप खाना बना रहे हैं तो उसमें थोड़ा स्वीट एंड सावर तो बना ही सकते हैं ना. उसमें स्वीट भी डाल दीजिए, सावर भी डाल दीजिए, दोनों बना दीजिए. तो मेक इट इन अ सिंगलेट स्टेट. ओके, so when you make it in that singlet state, all that you can demand is that उसका net angular momentum zero होना चाहिए, net magnetic moment zero होना चाहिए. You cannot demand कि ये x direction में up है, or for example y direction में up or down. It can be in the z direction, or it can be in the y direction. It can be in the z direction, or it can be in the x direction. It can be anything. When you write the wave function of the singlet state, it has no information on whether वो x में plus minus है या y में प्लस माइनस है या z में प्लस माइनस है. ओके, तो वो वेव फंक्शन जैसे अब जब आप लिखिएगा मैथमेटिकली तो उसमें कोई इंफॉर्मेशन रहेगा ही नहीं. यही इंफॉर्मेशन रहेगा कि उसका नेट एंगुलर मोमेंटम जीरो है.
Yes.
तो आइंस्टीन का आगे कहना था. हाँ, बस इतना. इसका मतलब हुआ ये है कि अगर हम उसको अब अलग कर दें तब क्या होगा, और एक पर हम मेजरमेंट करें, दूसरे पर ना करें. एक को हम एक को हम पीट दे और दूसरे को कुछ नहीं, दूसरों को भी चोट लगेगी. ऐसे
any more question from any other participants? Okay.
एक पोएट्री है इस पर, मतलब वो जो मजाकिया पोएट्री नहीं होता वैसे है. टू इलेक्ट्रॉन्स क्लोज कपल्ड एट स्टार्ट. दो इलेक्ट्रॉन को लीजिए नजदीक रखते हुए सिंगलेट स्टेट में. टू इलेक्ट्रॉन्स क्लोज कपल्ड एट स्टार्ट flew several parseconds apart. Parsec मतलब कि several light years apart. Said one in distress, what I am forced to express, what you are forced to express removes any choice on my part. मतलब अगर जो पहले वाले करता है तो दूसरे वाले को कोई चॉइस ही नहीं रह जाता. उसका ठीक उल्टा होना चाहिए. ऐसे वो कह रहा.
So it was really a very nice lecture, very informative. Pramen sir.
Yes, Himanshu.
You're there. So now can you conclude? Sir का हो गया.
So thank you very much, Himanshu. And from the RC19, being a secretary of RC19 Bihar, I'm very much thankful to our today's speaker, Professor AMARENDRA ji, keynote address. PK AHLUWALIA ji, he is presented this very webinar. And our respected sir and eminent physicist, Professor VIJAY SINGH ji, which this very lecture I was listening, and I am on the way from university to the Patna. So that's why it may be possible a few places may internet problem arise. So in that very case, I'm sorry to simply say before my saying something about today's lecture. So am I audible? In that very case, if time is over,
Yes,
so
sir.
that will be better to simply give me the other day, because the today's lecture, the Vijay sir lecture in the 4 parts, I want to conclude with this very remark, sir. I was also interested to ask a few questions to sir. but the way in which he has the represented the four, the simply, do you have the 5 minutes for me?
Yes, please, sir.
So in that case, in today's lecture of the Vijay sir, he has not only introduced the why quantum mechanics and how quantum mechanics is going to be the way in which with the help of the 4 slides, he has explained the several things, particularly the APR paradox, the last one. So he has introduced in the undergraduate classes, what happens, most of the students are very much puzzled and the complex to understand what is the quantization, what is quantum mechanics, and like this. So in that very case, it is because in most of the cases, most of the teacher and the books are simply referring the quantum means the discreteness. Anything is discrete, that is or discrete appearance is the quantization, like this. While in some textbook the definition is there like this. This is the study of the material, interactions of the material and the energy for the atomic and the subatomic particles for the quantum mechanics. But sir has given not only the example, the wave particle duality of the de Broglie, the Einstein hypothesis, rather the way in which the spin of electrons mechanism and that very point is very important for the particularly school going students and the undergraduate students, because there is most of them having the very much misconception regarding the spin of the electron. They think like that is spin having the some space and it is moving clockwise or anti-clockwise directions and like this, and having some inertia for the angular momentum. So sir has simply clearly demonstrated the things. Spin, electron, neutron, proton, any subatomic particles having spin means it has angular momentum, and the magnetic moment is your simply charge upon the 2m times of the angular momenta or current times of the area. So today's lecture, Himanshu, because we have not too much time, I'm very much thankful to the today's speaker. AMARENDRA sir has introduced in very good manner why we are going to celebrate quantum quest big in online way and the offline later on. And PK AHLUWALIA sir has participated today on our request. So from the RC19, we are very much thankful to all our today's resource persons, and very much thankful today's speaker, particularly the VIJAY SINGH sir. He has given his lecture very clearly and rather very much fruitful for we and our all participants and students. Thank you very much.
Thank you, sir. Thank you so much, sir. So I think yes, sir.
कल किसका लेक्चर होगा जरा बता दीजिए, कितने बजे होगा?
कल 5:30 बजे से शुरू होगा.
हाँ, who will lecture?
प्रोफेसर प्रमेंद्र कुमार वाजपेयी सर का है.
अच्छा. ओके.
कल सर वाइस चांसलर साहब का है जेपी यूनिवर्सिटी का.
ओके. प्रोफेसर प्रमेंद्र वाजपेयी, राइट?
जी.
ओके.
जी परमेंद्र कुमार वाजपेयी.
और कोई कुछ दिनों 5 बजे से शुरू होगा बोले ना. जस्ट टेल एवरीबॉडी सो दे नो व्हाट टू डू.
Sir, why not Himanshu going to share your all programs to all participants? In that very case, that will be वो ज्यादा यूजफुल रहेगा. और
हाँ, तो एक बार फिर से दोहरा दीजिए. तो कितने बजे से होगा रोज? कल 5 बजे से?
कल का प्रोग्राम 5 बजे 5:30 बजे से है.
अब परसों
सिर्फ 2 दिन 13 तारीख और 14 तारीख का प्रोग्राम 5 बजे से शुरू होगा.
अच्छा.
ये सारे प्रोग्राम जो हैं वो 5:30 से 6:30 के ही. सिर्फ 2 दिन 13 और 14 तारीख सैटरडे संडे है. वो दोनों प्रोग्राम जो है वो 5 से 6:30 का. और
5 से 6:30.
5 से 6:30 इसमें
ओके.
15 तारीख वाला प्रोग्राम भी हो सकता है, आधा घंटा ज्यादा एक्चुअली, लेकिन वो अभी तक फाइनलाइज है.
अच्छा, ठीक है. ओके.
So with this now we can conclude the session. So thank you everyone, thank you all the participants. I request you all, the link will stay the same for all the days. You can join this program and take the benefit of it. Amrit sir, can I conclude or you want to say something more?
No,
I think Santosh sir is here. Santosh sir.
नहीं है.
है वो आजकल. So with this, thank you so much. Now you can conclude. Now you can leave.
ठीक है. Okay, bye.
Okay, bye all of you.